Class 10, Chapter 1, Real Numbers, Exercise 1.1, Question number 1. Use the Euclid's division algorithm to find the HCF of the following numbers. The pair of numbers are 135 and 225, 196 and 38,220, 867 and 255. Now, one might think, why we need the Euclid's division algorithm when we already know various other methods to find the HCF of two numbers, such as the prime factorization method. Now, let us clear this doubt with the help of an example. Let us take the numbers 196 and 38,220 and find their HCF using the prime factorization method. For doing this, first we must find the prime factors of both these numbers. Taking the number 196, we will try to divide it with the smallest prime number, which is 2. Since 196 is divisible by 2, we move on to the next step, where we get 98. Again, we will divide 98 by the smallest prime number. 98 is divisible by 2. Hence, we move on to the next step, where we get 49. Unfortunately, 49 is not divisible by 2, because 49 is not an even number. We check the divisibility of 49 with the next prime number, which is 3. A number is divisible by 3 when the sum of its digits is divisible by 3. The sum of digits of 49 is 4 plus 9 equals 13. Since 13 is not divisible by 3, therefore 49 is not divisible by 3. We move on to the next prime number, which is 5. 49 is also not divisible by 5 because it does not end with the digit 5 or 0. We move on to the next prime number, which is 7. We know that 49 is a multiple of 7, which gives us 7. Now, 7 itself is a prime number. Hence, the only prime number which can divide 7 is 7 itself. Now, moving on to the number 38,220, this number is divisible by 2, which gives us 19,110. 19,110 is also divisible by 2, which gives us 9,555. This number is not divisible by 2. Hence, we check its divisibility by the next prime number, which is 3. To check its divisibility by 3, we must find the sum of digits of 9,555, which is 24. Since 24 is divisible by 3, 9,555 is divisible by 3 and gives us 3,185. 3,185 is not divisible by 2. We will check its divisibility by 3 by finding the sum of its digits. The sum of its digits is not divisible by 3. Therefore, 3,185 is not divisible by 3 as well. Moving on to the next prime number, which is 5, we know that this number is divisible by 5 because it ends with a 5, which gives us 637. Now, 637 is not divisible by 2. We will check its divisibility by 3 by finding the sum of the digits. The sum of its digits is also not divisible by 3. Hence, we check its divisibility by the next prime number, which is 5. It is not divisible by 5 as well because it does not end with the digit 5 or 0. Hence, we move to the next prime number, which is 7. Now, how to check the divisibility by 7? Let us see. We will multiply the last digit of this number by 2 and then find its difference with the rest of the number. For example, in 637, we will multiply 7 with 2, which gives us 14. We will then find the difference of the rest of the number, which is 63, and 14, which gives us 49. Since 49 is divisible by 7, therefore the number 637 must also be divisible by 7. On dividing 637 by 7, we get 91. 91 is not divisible by 2. We will check 91's divisibility by 3 by checking the sum of its digits. Again, it is not divisible by 3 because 10 is not divisible by 3. Moving on to the next prime number, which is 5, 91 is also not divisible by 5 because this number does not end with a 0 or a 5. Hence, we check with the next prime number, which is 7. Again, we will multiply the last digit of 91, which is 1, with 2, which gives us 2. We will then find the difference of 2 with the rest of the number, which is 9. The difference we get is 7. Since 7 is divisible by 7, the number 91 is divisible by 7. Dividing 91 by 7, we get 13. Since 13 is a prime number, the only prime number which can divide 13 is 13 itself. Hence, we have found the prime factors of both these numbers. Then, we have to write these numbers as a product of their prime factors. 196 equals 2 into 2 into 7 into 7, which is 2 square into 7 square. 38,220 equals 2 into 2 into 3 into 5 into 7 into 7 into 13, which is equal to 2 square into 3 into 5 into 7 square into 13. HCF is the product of the smallest part of each common prime factor in the numbers. The common factors in these two numbers is 2 and 7, and the smallest powers are 2 square and 7 square. The HCF will be the product of these two numbers, which is 196, and hence 196 is the HCF of the two numbers 196 and 38,220. So this was the entire process followed to find the HCF of these two numbers using the prime factorization method. We saw that it is a cumbersome process. So let's use the Euclid's division algorithm, which will make it easier for us to find the HCF of larger numbers. But to understand the Euclid's division algorithm, we must understand the Euclid's division lemma. So let's see what it says. According to the Euclid's division lemma, if there are two positive integers a and b such that a is greater than equal to b, then there exist two unique integers q and r such that a equals b times q plus r, where r is greater than equal to 0 and less than b. Now let us understand what these terms a, b, q and r represent. If we divide the two numbers a and b, this is how we do it using the long division method. Here, a is the dividend, b is the divisor. When a and b is divided, we get q as the quotient and r as the remainder. Now let us see how we can use the Euclid's division lemma to find the HCF of two numbers. Let the two numbers be a and b. First, we have to apply the Euclid's division lemma to a and b. That is, we will take a as the dividend and b as the divisor. We will find two whole numbers q and r such that a equals bq plus r, where r is greater than equal to 0 and less than b. We move on to the next step, where we check if r is equal to 0. If r is equal to 0, b will be the HCF of a and b. But if r is not equal to 0, we will apply the division lemma once again, but this time to b and r, where b will be the dividend and r the divisor. We have to continue this process until we get the remainder as 0. The stage at which the remainder is 0, the divisor at that stage will be the required HCF. This algorithm always works because the HCF of a comma b is equal to the HCF of b comma r for every pair of consecutive steps. Now let us apply the Euclid's division algorithm to the numbers given to us. The first pair of numbers are 135 and 225. Since 225 is greater than 135, we will take 225 as the dividend and 135 as the divisor. Dividing these two numbers using the long division method, we get the quotient as 1 and the remainder as 90. 225 can be represented as 225 equals 135 into 1 plus 90. We see that the remainder is not 0 at this stage. Therefore, we move to the next step, where the dividend will be 135 and the divisor will be 90. Dividing these two numbers using the long division method, we get the quotient as 1 and the remainder as 45. Hence, we move to the next step, in which the dividend will be 90 and the divisor is 45. Dividing these two numbers using the long division method, we get 2 as the quotient and 0 as the remainder. 90 can be represented in the following manner. Now, we see that the remainder at this stage is 0, which means 45 divides 90 exactly. So, the HCF of 90 and 45 will be 45. We saw that by Euclid's division algorithm, the HCF of A and B is equal to HCF of B and R for two consecutive steps. So, the HCF of 135 and 90 is equal to the HCF of 90 and 45. Similarly, for step 1 and 2, the HCF of A and B will be equal to the HCF of B and R, which means the HCF of 225 and 135 will be equal to the HCF of 135 and 90. Therefore, we have our required answer. The HCF of 135 and 225 is 45. Moving on to the next pair of numbers, which is 196 and 38,220. Since 38,220 is the greater number, we will take this as the dividend, and we will take 196 as the divisor. Dividing these two numbers using the long division method, we get 195 as the quotient and 0 as the remainder. Therefore, 38,220 can be represented as 196 times 195 plus 0. Since the remainder is 0 in the first step itself, we don't need to move further, which means 196 divides 38,220 exactly. Therefore, we have the required answer, that the HCF of 196 and 38,220 is 196. Moving on to the next pair of numbers, we have 867 and 255. Since 867 is greater than 255, we will take 867 as the dividend and 255 as the divisor. Dividing these two numbers using the long division method, we get 3 as the quotient and 102 as the remainder. 867 can be represented in the following manner. We see that the remainder is not 0 at this step. Hence, we move on to the next step, in which the dividend is 255 and the divisor is 102. Dividing these two numbers using the long division method, we get 2 as the quotient and 51 as the remainder. 255 can be represented as 102 into 2 plus 51. Since the remainder is not 0 at this step, we move on to the next step, in which dividend will be 102 and divisor will be 51. Dividing these two numbers using the long division method, we get 2 as the quotient and 0 as the remainder. 102 can be represented in the following manner. Now, we get the remainder as 0, which means 51 divides 102 exactly, and 51 is the HCF of 102 and 51. We know by Euclid's division algorithm, the HCF of A, B is equal to HCF of B, R for every pair of consecutive steps. Therefore, the HCF of 255 and 102 will be equal to the HCF of 102 and 51. Now, if we consider the steps 1 and 2, We know that Euclid's division algorithm is true for every pair of consecutive steps. Hence, it will satisfy HCF of A, B equals HCF of B, R, which means the HCF of 867 and 255 will be equal to the HCF of 255 and 102. And we have our required answer. The HCF of 867 and 255 is 51. We have found the HCF of all the three pair of given numbers.